Okay, so in this section we're continuing one last section in section 3. Or chapter 3. That's section 3.10, which is linear approximations and differentials. Okay, and so this really starts our applications of the derivative section. And so the first thing we want to think about is if you have some nonlinear function, the idea is that at a point A, the function looks approximately like the tangent line, right? So this is my function f of x, this is my tangent line, and so what we're saying then is close to the point A, let me get a different color there, if I'm close to the point A, right, that means if I take a look at my function in this box here, oops, maybe here, then the function itself, the curved line, or the curve itself, looks very much like this line, right? And so I can use so the idea is that you can use the tangent line to approximate the function. And in fact, the approximation is exact at the point A, f of A. Okay, and then we see that as you move away from the point A, right, the difference between the line and the function starts to grow, and that's pretty common. Okay, so our approximation we're going to use, well, let me change back to white here so you can see, we can use the tangent line to approximate f of x at a point, and we'll say a f of a, just to emphasize, right, that we're at this point on the graph. Okay, let's see, do we know how to do that already? I think we do. The tangent line, which I'll call L, so L of x is the tangent line it's going to be the tangent line. Actually, let me write the tangent line over here, maybe. The tangent line, remember, is given as y minus f of a equals f prime of a times x minus a, and I'm writing this over here because I'm going to bring the f of a, or add f of a to both sides to rewrite it over here. So over here I'm going to have f of a plus f prime of a times x minus a. Okay, and so this is the tangent line approximation. And so what we're saying is we can approximate f of x using L of x. Okay, or you could say L of x, f of x is approximately equal to L of x at x equals a. Okay, good. All right, so let's do an example. Approximate the square root of x plus 6 at x equals 3. So using linearization is what we're going to call it. Linearization. So to linearize the function means to use the tangent line approximation for the function. Okay, so the solution here, if x is equal to 3, we need y. So f of 3 is equal to the square root of 3 plus 6. Square root of 9 is 3. Okay, so we're at the point 3, 3. And now we need the slope. The slope is going to be f prime of x, which will be 1/2, right, times x plus 6 to the minus 1/2, right? That's from the square root function. And then times the derivative of the inside function, but that's just going to be 1 in this case. Okay, so if I rewrite that, that's 1 over 2 square roots of x plus 6. So if I evaluate this at 3, I get 1 over 2 times the square root of 9, which is 1/6. Good. So now I've got the point that the line goes through and the slope. And so my L of x in this case is going to be 3 plus 1/6 times x minus 3. Okay, good. So what does this graph look like? If you were to graph this, the square root of x plus 6, maybe I shouldn't write it right there. The square root of x plus 6 looks like the square root of x shifted back 6 units, right? So it's going to look something like this. This is minus 6. And then at 3, right, we're going to have a line right there. And so the line comes this way. Okay, and so this is our, maybe I should write the line in a different color. I'll put the line in red. Oops. Everything's going off here. There's my line. Okay, close. That's pretty close. Good. So you see how we can use the tangent line here. And in fact, the tangent line approximation is pretty good. In fact, for a couple units back and forward, the tangent line approximation is pretty good. And you could see, so the error, right, would be the absolute value of the difference between f of x and the line, right? And so you could write down the error function in this case. That would be the absolute value of the square root of x plus 6 minus, and then we can write our line, right? And so you could actually plot this if you wanted to. If you plot that in Wolfram Alpha, for example, you could see how close you are. In fact, if you do plot it, and you know what? I'm going to pause the video right here and set up Wolfram Alpha, and then we'll be back when we get Wolfram Alpha set up and plotting. Okay, so I'm back with the plot from Wolfram Alpha. So that is wolframalpha.com, and so you can see the command there, and Wolfram Alpha will go ahead and plot that for us. And so you can see, right, that things are looking pretty good. The solution is exact here at 3, but then, whoops, I don't know if I can annotate this. Well, that's okay. You can see here that the error is really small for x in a pretty wide range from like 2 to 4, right? So if you wanted the error to be within 0.02, right, that you could go from like 1 to almost 5, right? So anyway, this is one way you could plot the error function, the difference between the function and your line. Good. All right. And so, by the way, this shape that you're seeing here, where it's exact at 3 and then it goes up on either side, so it looks kind of locally quadratic or locally like a parabola, that's going to be on purpose, right? Because our line is always going to be exact at 3, and then the error builds out as you go further and further away. Unless your original function is a line, of course, because then the error would be 0 everywhere. Okay. So let me pause there and get back to the other. Okay, so we're back and we've got one more example. So example, approximate the square root of 9.5 using the linear approximation, or the linearization, I should say. So how would we do that? So remember that our f of x was the square root of x plus 6, and we know that our L of x is 3 plus 1/6 times x minus 3. Okay, and so if we want to approximate something like this, right, you want to look for the base point, or where we're basing our approximation on this. So in this case, right, our x was equal to 3.5, right? If I want to do that, so solution, I would use x equals 3.5. Okay, and so therefore, when I go over here, I'll have 3.5 minus 3, so that'll be 1/2, and so my approximation will be square root of 9.5 is approximately 3 plus 1/6 times 1/2. Okay, and so that's 3 plus 1, 12. Okay, and so that's approximately equal to 3.0833. So you might ask, well, how good is that approximation? Well, using our calculator, we can go ahead and see what the square root of 9.5 is. The square root of 9.5 is approximately 3.082207, and so on. And so you can see the difference, right? This is our linear approximation, and this was what our calculator said the square root was. And so you can see those are really close together. Now, of course, you also see the main question that you might be thinking to yourself, and that is, why would I approximate the square root of 9.5 using a linearization when I can just compute it on the calculator? Well, this is just an example where you actually can compute f of x on a calculator, but there are instances, right, if you're, for example, if you only know your function by data points, then you are not able to make this kind of exact evaluation, right? And so you end up having to use some kind of approximation. And so we'll talk about those kinds of approximations later. For right now, though, it's nice to be able to compare the exact value versus our linearization, just to make us feel good about our approximation and make sure that this is actually doing something. Okay, so there's one more video left on this about some notation that we want to use in this section, and it's notation that you'll see a lot in different places, so I think it's important to spend a little bit of time talking about it. Okay, I'll see you then.